Hi, everybody. Good to see you again. We are here today for our final part of a three-part series titled Accelerating Battery Manufacturing Scale-Up by Catching Early Quality Issues with UHPC. My name is Kevin Wood, and with me today is Stephen Glazier. So if you've been attending these, this is well by this point, but my name is Kevin Wood. I am the Director of Consulting here at Voltaiq. My background is that I've worked in a variety of different avenues within the battery sector, everything from being a professor working on lithium metal, silicon anode, solid state electrolytes, to being a CTO of a solid state startup company. And really what I focus on at Voltaiq is trying to help engineers make the most out of their battery data. All right. So this includes things like education, consulting services, those types of things, and also helping work towards an understanding advanced research that we can do into understanding the data, how we can analyze that data, how we can make the most out of the information that you get when you're actually charging and discharging and testing your batteries. So that's my background, and I'll quickly pass it over to Stephen for his intro.
Hi, everyone. I'm Stephen Glazier, Director of Technology at Novonix Battery Technology Solutions. I've been here for about 6 years after completing my master's and PhD with Dr. Jeff Don at Dalhousie. And my real focus here is helping our internal and external stakeholders in their R&D programs. So leveraging our battery prototyping facility here. We have a little pilot line and our test facilities with a few thousand battery test channels, really engaging with those internal teams for our materials businesses and external teams to help scale up technologies. And then also working with our UHPC, or Ultra Precision Coulometry group, which we'll be talking about today.
Awesome. All right. So with that, let's jump right into this, right? So this session is really going to focus on manufacturing and how do we try and address a lot of the challenges that battery manufacturing is facing currently. I think probably most of you are all aware that battery manufacturing and scaling battery manufacturing is incredibly challenging. This may not have been quite as known to everybody back 5 years ago, but now we've really seen a lot of these consequences, right? So what kind of causes a lot of these issues that we've seen? And one of the things is a really slow yield ramp. So actually getting to the point where you can make enough cells to become profitable is really difficult. So we've seen numbers as high as 84% scrap from these gigafactories in the first year that they are, supposed to be online. So 84% scrap. Margins are so slim in the battery manufacturing space. This is a real killer. So the longer you stay in this high scrap environment, the more challenging it's going to be for you to sustain and stay afloat as a company, right? And a lot of times it takes greater than 4 years for these organizations or for these gigafactories to get to a point where they can actually become profitable. And I'll show some examples of that here shortly. Another thing is that quality issues really kill your profitability and become something that we have to address, right? So you have to address those issues and you have to identify those issues as quickly and as accurately as possible and get to the root cause of those issues and really understand what's happening mechanistically with your system to be able to address those well. So a lot of times these are ongoing scrap rates that we see once a gigafactory has been spun up and is actually running. A lot of times there can be greater than 10% scrap rate, even when a facility is up and fully operating at steady state conditions. And then if there's recalls or safety concerns or issues with those batteries as they've come off the line, this is going to cause billions and billions of dollars once these things actually hit consumers' hands. So you have to be able to address those things and figure out what cells are going to cause problems. Maybe I can't identify them right away. They're going to cause problems later on down the road. How do I try and identify that? And those are some of the big questions and big challenges that are really hindering the battery manufacturing space currently. So I'll keep these a little bit ambiguous here, but if you dive in and look at the links that I have provided down below, you'll be able to figure these out. But there was a North American gigafactory, started production in 2017. There was about 4 years of really difficult ramping and actually scaling and getting to this process where it was able to become profitable. And then by 2021, they were able to maintain profitability. Okay. There's a European gigafactory that started production in 2018. And through 2023, these production issues have continued to exist. There's been missed deliveries, vehicle recalls, really long, arduous process of trying to get that factory up towards scalability. And then in late 2021, there was a Scandinavian gigafactory that started started production, had difficulties ramping everything for the next several years, and then eventually filed for bankruptcy in Q4 of 2024. So you see that there is a long kind of littered past of gigafactories and challenges that gigafactories have faced as they've tried to get to the point of profitability. And that's really what we're here to discuss today is how are there ways that we can try and improve that and address those issues. So why the failure to launch, right? Why do we have these issues in the first place? And I would come back to the fact that I think it really stems from a data issue. And here's my motivation for that, right? My motivation for that is that it takes weeks to potentially even identify a problem. And we'll go through that. But if you're talking about delta V values and some of these standard metrics, it can take weeks to identify the problem. Once you've identified that problem, it can take months then to perform root cause analysis, right? And once you've performed that root cause analysis, it can even take years to improve the process because you don't necessarily understand why those things happened. There's a lot of things that can be hidden there. So we really have to try and work on figuring out and identifying the problem as quickly as possible, performing root cause analysis to the point where we're actually able to mechanistically understand the problem. Then we can improve the process. So if you remember back to the last webinar that we talked about, I showed this graph, and I think this is a really helpful visual for helping to understand a lot of the challenges that we face in the battery industry. A lot of times we focus on these top level metrics, and I call this like the tip of the iceberg, right? This is things like cycle life, capacity, safety, voltage fade. There's some of these really easy to see top level metrics that really get all of the attention, right? This is probably what most of the metrics in a gigafactory are based on, right? What's my capacity after the first charge? What's my internal resistance after this step? What's my voltage fade like? These are really the metrics that help us to determine whether a battery is good or bad. But at the end of the day, it's really the process. It's really what's underneath the surface that really helps you understand if you're going to be accessible. It's what is the data quality of what's coming in? Are you fully analyzing that data? Do you have the ability to do correlation analysis and link all of that to process and metadata? Do you have understanding of slurry and quality challenges from what's coming into the actual process? Do you have traceability, right? And ultimately it's getting down to, do you really mechanistically understand how the process is working and what could be causing problems when it actually gets to, you've turned the lights on and now the battery is starting to try and be cycled, right? It's actually working electrochemically. Do you understand mechanistically all of the things that have gone into that and where potential problems arisen from? So really, a lot of times I think people focus on that tip of the iceberg, and it's really, there's a lot more under the surface that we really have to try and fully understand to be able to make good informed insight as to how to move forward with battery manufacturing and the process tweaks and all of the things that can go wrong and how we actually get to profitability and scalability as quickly as possible. So why the failure to launch? It's a data issue, right? So the tip of the iceberg, if you're just focused on the tip of the iceberg, you're identifying problems in weeks, you're performing root cause analysis in months, and you're improving the process over years, right? Rather than if you're focused on what's below the surface, right? This helps you to be able to identify the problems in hours, perform root cause analysis in days, and potentially improve your process in weeks. This is really helping you get to that scalability point as quickly as possible. So make sure that if you're in the area of working in battery manufacturing, you have to uncover that iceberg. You have to make sure you're getting to mechanistic understanding and you're really understanding the root causes of all these things, getting as much data in as you can, making sure that no stone is going unturned, so to speak, and you're really able to try and maximize the insight that you're getting from all of the information that's being collected around your manufacturing facility. So here's the idea of quick visuals of what Voltaiq is really trying to do, right? There's this typical path that you go through here as a new factory, right? And you have this point where you have to break even. And we really just want to try and shorten this process. You're still going to go through this, right? This is an inevitable point of every battery manufacturing process. A lot of times I hear about, we're just going to copy and paste a line from Asia and put it in North America, or from Europe and put it in North America, or from North America and put it in Europe, or whatever it is. And whenever you do that, the machines are a little bit different. The source material is a little bit different. Everything's a little bit different. And all of those things create this point where it's difficult to scale that process. And Voltaiq is really focused. And what we're talking about in this webinar is really focusing on methods and strategies to help you try and get to that break-even point sooner than you would normally and as quickly as you possibly can. Okay. And then for existing factories, right, there's this typical path. You eventually reach steady state and you reach this profitability point, but there's a gap here, right? There's a gap between what's possible and what you're currently operating at, right? If you don't have the best metrics, some cells are getting out that probably shouldn't, and maybe some cells that could get out aren't, right? And how do we try and optimize the cells that get out into consumers' hands and make it so that you have the highest amount of yield that you possibly can with minimizing any sort of warranty and return issues? So here's when we look at a battery manufacturing process. This is a typical way of looking at that, right? So you go from materials QC all the way to filling right before formation, right? This is when the battery kind of comes to life, is right here at this, when the cell is finally finished. This can take about 3 to 6 hours. And then if you go through this whole formation, aging, QA process, this can take almost a month at times to go through this entire process. And if it's at that point that you're determining whether a cell passes or fails, right, you have wasted a very long amount of time before you're actually understanding, did my cell work or did it not? And if you have a problem that's coming in your mixing process or in your calendaring or your slitting or wherever, it's almost weeks, right, until you've even identified that you have a problem, which is going to then make a whole bunch of wasted material in the cells that was made in between that time. So key challenges here, you don't know cell quality until weeks after it's produced, and then thousands of upstream process parameters and tolerances must be finely tuned to make it so that you don't have quality issues. And how do we navigate that complex landscape? So here's where Voltaiq is really coming in, is that we want to try and help you identify that problem sooner. And then we also want to be able to help link the electrochemical data that you're getting, formation, aging, QA, all those sorts of things. We want to link that information, and we want to be able to create traceability back to these different processes. That really helps aid in that root cause analysis, taking that down, right, from months to potentially weeks, right? That's really where that comes in. So I figured the best way to show this is to actually be able to pull this information up for you. So I'm going to go ahead and share this. Okay, so here we are. This is the Voltaiq platform. So the Voltaiq platform allows us to be able to bring in really easily a whole bunch of different tests by essentially finding some sort of parameters, right? We can search by strings, by lot numbers, by date ranges, anything that you're interested in. We can search and organize and bring in lots and lots of different test records here. So for this example that I'm showing you right here, I've selected 10,000 different test records for over 5 different lots of materials. So each data point right here represents one cell. And the electrochemical metric that I'm focused on is actually just a really simple metric right now. We're just going to focus on a delta V value just to demonstrate how Voltaiq does this with metrics that everybody understands, right? So the delta V value, a cell is made, they check the OCV, then it's let rest for a few days or weeks, then you check the delta V value, or check the OCV again, and you see how much that value has actually changed during that resting process, right? And then that delta V value helps you understand if you have some sort of short or some sort of issue within the cell. So here we're able to plot up these delta V values and bend them by different lots of material right here. So we can see that these first 3 lots of material seem to behave pretty well. Then by the time we get to lot 4 and lot 5, we see that we have an increasing tail of values that have higher OCV, cells that have OCV, higher OCV values. So what's the reason for this? And what's actually going on here? So we can plot these versus a histogram and really start to see that some of these there's a tail of cells that have a higher and higher count of material over here that's starting to have these higher delta V values. So this is just noticing the problem. We have the ability to automatically create alerts on this information. So if I zoom up here, you can see that for these 2 different groups of material, or for the 2 different lots of material, here's like one that looks like it's in the control group. This is normal behavior. Here you're now starting to see delta V values that are a lot higher than normal. You can see that I have an alert set. So right here at this value of 225 microvolts is essentially where I'm starting to get alerts. I've set this up as my control threshold here. So all of these cells here we would reject. There's much, much fewer over here that get rejected. So why did this specific lot of material have so many issues? So where Voltaiq comes in is we have some correlation analysis and all sorts of different tools that can help you identify potentially areas of root cause. And one of those things that we can do is we can actually then take those specific process parameters, right? In this case, we're talking about cathode slurry mixing equipment and the delta V value, so the electrochemical value right here. And we can link these together. So now we can actually see each line in this parallel coordinates plot is essentially like a battery. And so if this battery had a really high delta V value right up here, let's say like 350 microvolts, then it came from mixer 2, there would basically be a line from that cell over here, just creating this traceability map of like how the electrochemistry was performing to how the process parameters that were associated with that specific cell. So as I move up and down here, you can see that these high delta V values came from the same mixing equipment. Then when I was here in this optimal range, it was all coming from the same mixing equipment. So mixing equipment doesn't seem to necessarily be correlated very well with these delta V values. Okay. Conversely, if I come over here and I look at this delta V value over here and I compare this with the actual slitting equipment, you can see as I get up to these high delta V values, they're almost entirely coming from slitter 1. Then I have a little bit that's coming from slitter 2. And then by the time I get down here to these low values, predominantly most of these are coming from other slitting equipment. There's this distribution here where these high delta V values are really coming from a couple slitters. You can slice and dice this differently here. You can put the electrochemical metric in the middle and the two different process parameters on the outside, once again, revealing the same thing. Doesn't seem like there's any correlation in mixing, but you can clearly see the correlation between the slitting equipment down here. So now if I plot instead of by lot, if I plot by slitter over here, you can see that now the electrochemical values associated with slitter 1 and slitter 2, these delta V values are much higher for slitter 1 and slitter 2. So where is this actually coming from? We can take this down, dive into the data a little bit further and figure out that lot 4, the one that we really saw most of the problems coming from, and even lot 3 that we saw some of the other problems coming from, had the highest age, basically the slitting blade had cut the most amount of material at that point. So this is really helping improve that process and telling you, hey, you need to replace the slitter blade more frequently, maybe at 3 million kilometers or something like that, so that you're not actually getting to these really high numbers where you're going to start to create more and more potentially of these burrs that are then causing these high delta V values. So this is just to give you a quick overview of how Voltaiq helps solve some of the problems within the manufacturing space. Here's to summarize that in one graphical fashion. Here's what Voltaiq does. We try and alert you, and so that not necessarily a person is looking at it, but you can automate and set these different process controls and electrochemical thresholds, right, to help identify battery defects faster. Then because we've linked all of that data to all of your processing data, it helps you understand the full context of the issues, get really detailed information about how the traceability of those poor performing cells are linked to what's happening in your manufacturing process. And then from there, we can quickly diagnose, because all that information is there, we can quickly diagnose the root cause of the issue, right? And then we have all of the tools and the graphs like I was showing you. Those can easily be shared, downloaded as reports, anything like that to help you quickly communicate how you resolve the issue that you're having in your battery and your manufacturing facility. So now this kind of tells you how, just even with standard electrochemical metrics, right, Voltaiq helps try to accelerate these issues. One of the things that we really want to do, and where Voltaiq is an expert, is we're experts at helping understand the actual electrochemistry and getting you from some of those just really general capacity and delta V and internal resistance and some of those general metrics. We want to try and actually help you figure out more quickly with advanced metrics and advanced electrochemical insight, right, where things are going wrong and help aid in that root cause analysis. So this is identifying things faster and helping you understand the root cause of these issues more expediently. So things that we offer can be correlation analysis, rest step analysis, advanced DQDV, advanced coulometry, UHPC calculations, and Stephen will go into detail on how UHPC can be used here in the manufacturing process. But a lot of these metrics, what they really do is they help you understand certain aspects of the electrochemistry, maybe the thermodynamics, maybe the kinetics, maybe the transport, maybe corrosion reactions, right? They give you detailed insight into those specific processes that are occurring, which helps you really quickly aid in the root cause analysis, help you figure out what you need to address, really speeding up that time to profitability and making sure that the cells that are going out are the cells that really are going to be the best performing cells, and you're not scrapping cells you don't need to, and things that shouldn't be getting through the QA process, making sure that those aren't getting through the QA process. This is just a quick overview of how Voltaiq helps and how we integrate with some of these advanced solutions like what Stephen's going to talk about here with the UHPC. So with that, I will pass it off to Stephen.
Awesome. Thank you very much, Kevin. I'm just going to get myself set up here with screen sharing. Okay. So I'm going to be talking about specifically using Novonix's UHPC ultra-high precision coulometry equipment in this QA/QC step. And to do that, I'm going to talk about specific use cases by showing case studies, by showing real data that we've collected here using our pilot line and some of our internal and external engagements that we've had. So we're really showing, that where value has been realized in the real world. So I'll give a quick introduction to Novonix, talk a little bit about what quality issues in R&D and production that we find, talk about UHPC, and then how this is going to help with a couple specific case studies, talking about changes in materials, impact of moisture, and then even things like cell wetting, and then QC and manufacturing, touching on what Kevin was talking about with that case study within the Voltaiq platform, something fairly similar in how UHPC may be able to speed up this QC step that can usually take weeks or even a month in manufacturing. Novonix, for those that aren't aware, we span the whole battery ecosystem. So starting with our anode materials division in Chattanooga, Tennessee, where we're rapidly scaling domestic production of synthetic graphite for anode materials. So we've got offtakes with tier 1 manufacturers, and then our cathode materials division, which is over just up here in Nova Scotia, where I am, where we're commercializing our patented all-dry zero-waste cathode synthesis technology. And then paired up with the cathode team, we've got our battery technology solutions division, and this is where we have our prototyping facility where we can make pouch and cylindrical cells and really partner up with people from all over the industry to scale up technologies. There's a really good synergy with our cathode and anode materials divisions here, where they are also our customers of our prototyping line. So we help them prove out their materials. And this is also where UHPC is made and has been offered to the industry for about 11 years now, is in our BTS division in Nova Scotia. So I'm just going to be focusing on that UHPC part, and there's some ties back to our anode and cathode divisions here on how we really use this tool internally to accelerate our success in the industry. Like I said, I'm going to talk a little bit about what quality issues we see in cell development and manufacturing. Obviously, Novonix isn't a cell manufacturer, but we are a R&D and technology development company, and we have our own prototyping line. So this is all very close to us. So specifically in development, this is where we have less control than in manufacturing. So things like material and process consistency doesn't have as tight controls and tolerances as mass manufacturing. Environmental variability may be a lot more than in mass manufacturing. The ability for things to get cross-contaminated or little specks or bits of on slitting may not be as optimized. So there's more likelihood of contamination for materials. And then things like traceability, like Kevin was saying, and especially things like statistics are not as rigorous for traceability or large lot sizes in development. So these are all big considerations when we're doing this type of development work. And like Kevin said, Voltaiq really helps with this traceability, whether you're at manufacturing at mass scale or in this development scale. Quality considerations in mass manufacturing. So this is where we have tighter tolerances. We've got lot to lot variations for both materials and cells, equipment and line variability, as was shown earlier in that case study. And then really thinking about these long-term effects of very small defects. We're seeing, even in recent weeks, massive recalls of batteries with cells with very small defects that weren't caught in traditional QC. So really, how do we rethink QC and how can we use more advanced tools to do this? That's why we're here today. And that also brought up in that case study, speed of detection versus production. If it takes you 30 days to detect an issue, there may have been millions of cells made since then with those same parameters or conditions or materials. Similar to our last webinar that we put on, I want to talk with UHPC about what gaps exist using existing equipment or techniques in the field. And to start out, I just want to ask a question for everybody. There should be a pop-up on your window here. Which category best describes your role or your business function, just to gauge the audience and see where everyone's coming from today. Okay, perfect. So we've got a lot, about 60% of people are in the R&D field, and then process development seems to be next, about 15%. So I think all of this will be quite relevant to everybody in this group. Okay, so like our last webinar that we talked about, where UHPC is very useful in research and development, in QC and in manufacturing, the gaps that UHPC can help with are basically the same theme, is small things with big implications. Existing test equipment and metrics and techniques really excel at testing cells to end of life, doing rate capability testing, things where small errors of less than parts of a percent in your values really don't make a huge difference. Where these gaps are where these bulk metrics, errors of even fractions of a percent or less, can matter a lot. These are in things like material and environmental variations, detecting early QA and QC issues, trying to understand impacts of these issues in cells in a very short amount of time. If your measurement technique has an uncertainty or an error, precision, accuracy of this, and the things that you're trying to differentiate are in a range of about this, you'll always lose the ability to detect these things with your measurement techniques, because the resolution or accuracy just isn't there. So I'm going to go over just 2 slides from previous webinars that we've posted a little more quickly this time, just to make sure we're all on the same page. So when we're testing cells, thinking about UHPC, it's really important to understand what we're really measuring when we test a cell. The only thing we're truly measuring is voltage difference across the electrodes and the amount of electrons moving through the external circuit. We're not directly measuring anything going on inside. We have to infer based on those electrons. We count what's happening. So there's a couple contributions to counting electrons moving through these circuits and how they differ from charge discharge throughout cycling a cell. So one is when we lose capacity. So this can be SEI growth, active material loss, etc. Every cycle we'll be losing lithium inventory to certain reactions or mechanisms within the cell. And then every subsequent cycle will count fewer electrons. The more accurately we can do this, the more quicker we can detect very subtle changes happening in a cell. And that's fairly straightforward. For quality insights, this can let us learn things about the proper wetting of a cell or lithium plating that's happening, material variabilities, some pretty basic things. And this, when we think about coulombic efficiency, which I think everybody uses in their work, but maybe is not appreciated as much as it could be or broken down into its constituents, this loss of capacity means that we're counting fewer and fewer every subsequent charge discharge electrons through our circuits. And so our coulombic efficiency is going to be 1, a perfect cell, minus some kind of fade term. But then there's also more terms, more electron contributions that we have to think about as well, that are going to make a mismatch between our charge and discharge capacities. And so what we use as a term to talk about this is we call it a slippage term. This is well documented in a lot of papers dating back about 13, 14 years ago from the Don Lab at Dalhousie. And this extra term here, making a difference between charge and discharge, are for things like electron donating reactions, transition metal dissolution, things where in order to create charge balance in our cell, if we have a soft short or a short circuit within our cell, when we're starting to charge our cell, we create this electron shuttle within the cell and we count a bunch of extra electrons. We have manganese dissolution. In order to create charge balance in the cell, we actually have to count electrons through this external circuit. And of course, this is going to make this difference between charge and discharge capacity During discharge, all of these things look like a self-discharge process. In the middle here, I'm showing a reversible shuttle mechanism. This is similar to mechanisms that were published by the John Lab showing that PET tape was contributing to reversible shuttles within cells. And it was detected using UHPC to find these slippage-based mechanisms that persisted months and months into cell cycling. The ability to actually measure these types of mechanisms give a lot of interesting quality insights into things like contamination, physical defects, material variabilities, and environmental effects on the cell and the electrochemistry. So if we're able to very accurately count electrons and differentiate between these two different types of mechanisms happening, we can learn a lot more, a lot quicker. And just to talk about slippage a little bit and how we turn this into a cycling metric, we can picture this as if we're counting more electrons during charge than we do during discharge because of these electrons we overcount due to these mechanisms like this short circuit here. We have to put in more charge during charge to get the cell charged, and then during discharge we don't count as much charge because there is self-discharge happening in the cell. We're always going to have this shorter discharge than our charge cycle. What this means is if we charge our cell up and then discharge it down, we're not going to end up back at zero. And if we keep repeating this over and over again, we're going to surpass this endpoint, and our cumulative capacity curve is going to walk out to typically higher and higher capacities. And the rate at which it does this, if we're tracking electrons carefully enough and accurately, precisely enough, this rate that this curve walks out can tell us something about the rate at which those mechanisms happen. So we can see here a quick example where two different electrolytes with pair cells here, so it's very consistent, have very different slippage rates. One is multiple times faster than the other. And this is telling us that there's a lot of electrolyte oxidation happening at the cathode, and that this electrolyte 1 is probably not the best for these conditions of higher temperatures and higher voltages in these cells. So given that, I ran through these really quickly. Just want to gauge from the audience, how familiar are you with charge endpoint capacity slippage? If this is all new, somewhat familiar, or if you've been to all of the webinars and you've heard all this before. Okay, yeah, there's the window up on the screen. Okay, so a very even split across all three. Okay, great. So we're going to go into some case studies and really talk about using charge endpoint slippage and some of these other terms with a little bit more background before we get in there. So here we go. When we talk about Coulombic efficiency, of course, if we're going to be able to split up these terms and differentiate them, we need a tool that's able to measure Coulombic efficiency and its constituents very accurately and precisely. In order to do that, we need to track both current and voltage, again, accurately and precisely. The saying both accuracy and precision is very important there because those are two different things. So we can see here these other three cycler types that we have here in our labs. We actually have thousands of channels of cycler 3 and hundreds of cycler 2, and then hundreds of our own cyclers. You can see the difference when we put on a group of identical cells of tier 1 manufactured cells. This group on the Novonix UHPC has very tight Coulombic efficiency, very consistent, repeatable cell to cell. So this is really going to help us try to make these really accurate measurements very quickly and differentiate between cells. Because here, the noise and the inaccuracy of the cyclers is much, much bigger than the differences cell to cell, or even between a change that we may make to a cell. So we're going to lose that ability to differentiate between cells or chemistries with these other pieces of equipment. The way we do this is, of course, just being very accurate and precise with our measurements. So these other cyclers here, you can even see things like bit switching in the resolution of some of these cyclers and these 16-bit cyclers. Cycler 1 here, very good resolution, but poor accuracy. And then with Novonix, we have good for both. What this translates to when we think about cyclometrics for Coulombic efficiency, we've already shown this in the other plot where there's really large spreads between identical cells on these other cyclers, and then very, very consistent results on the UHPC. For something like capacity fade, this is something that's kind of cumulative over many cycles. And so you can see no matter what cycle we put it on, no matter what the resolution is, eventually we get that trend where we can see the capacity decreasing, or in this case, the fade increasing over time. And we use these metrics all the time. Why slippage isn't a very common metric is because it just isn't possible without that really high precision and really high accuracy. And you can see here that this slippage that we showed in the previous slide was very consistent on the Novonix system, but all these other systems, we're walking forwards in capacity, we're walking backwards in capacity. And this really comes down to the accuracy and also the bias between charge and discharge within these channels. If you're charging a cell and you're always slightly overcounting compared to discharge, you're always going to have this like basically fake slippage. And the more biased towards overcounting on charge you are, the higher your slippage is going to be. And if you're biased towards overcounting on discharge based on the accuracy spec of your equipment, then you're going to slip. Your charge on point is going to slip backwards because you're always going to have a larger discharge capacity than is real. So this is why slippage isn't necessarily a very used metric because it just isn't possible in almost any other type of cycling equipment. So where are the opportunities for QC? Really, this comes at decreased time and cost. Where can we use UHPC to fill those gaps? So inter and intra-batch statistics, so defining tolerance limits for some of these advanced metrics. If you were able to take just a small subset of cells, every lot of cells that's made, or every time a material is changed, and use some of these like very fine insights in a very small amount of time, you may be able to determine that there's some kind of change between lots as we're moving on, as the normal QC process is happening. This can be looking for things in self-discharge. This can be using DQDV because obviously with very accurate and precise voltage and current measurements, we get very clean DQDV type values. And then other types of techniques and advanced metrics, impedance and diffusion measurements, advanced modeling, lifetime prediction, etc. So I'm going to jump into a case study that I briefly covered last time, only talk a couple minutes about it before I get into some new stuff. So this will show the value of charge endpoint capacity slippage, these kind of invisible reactions on other cycling equipment that really matter long term. So here we've got two NMC 622 variations. These could be if you're switching manufacturer or even switching lots or shipments, and there's something different with that shipment of cathode material coming in. This is an application of this case study. So you can see here cycle aging on these 622 graphite cells that we made on our pilot line, cycling fine for 2,000 cycles, and then all of a sudden this group number one starts going into rollover failure. And then even looking at impedance values, looking at this delta V, in our case, delta V is average charge minus average discharge voltage of the cycles. There's actually no sign of anything going wrong here either until about 2,000 cycles. There was nothing in the data that we could see that would point to anything happening. So the hypothesis here is that UHPC data should be able to predict this behavior faster because we know something should be happening that's strictly related to reactions happening at the cathode. It's the only thing different between these cells. They're made on the same day, made with the exact same anode coating, exact same electrolyte batch, etc. You can see they perform very similarly. If we look at the UHPC results, you can see that just in about 20 cycles, but we can tell within about 10, which is only about a week of cycling, that this batch number two has very, very different Coulombic efficiency. It's a lot higher. Obviously, these cells are cycling a lot better somehow. But we didn't see that in the capacity fader. We didn't see that early in cycling. When we split CE into our fade component and our slippage component, we can see, as expected, there's almost no difference in capacity fade, which we expect based on the earlier results. But where we see this huge result happening is in charge endpoint capacity slippage. These mechanisms that are donating electrons at the cathode, typically electrolyte oxidation, transition metal dissolution, and this rate is about twice as high as this number 2 batch. So obviously there's something happening here that we can detect just in a few cycles very consistently and accurately. There's triplicate cells on these plots. So you can see how consistent these measurements are. So just within a few days, we're able to say, look, there's something wrong, there's something different with these cells, which actually took months and months before. So there's a lot of parallels with this to manufacturing, lot difference detection, environmental variations, and we're going to talk about environmental conditions next. Impact of moisture, I was talking a little bit about in the development world. We don't necessarily have the really fine constraints that we might have in manufacturing or controls over things like the environmental conditions, humidity. Speaking as somebody that works in a coastal area that can get quite humid in the summer and quite dry in the winter, this is something that hits pretty close to home. With a cell prototyping line, with most of our operations in dry environments and some not, it is something that we have to consider very carefully. In terms of manufacturing, there can be environmental conditions that change transportation of materials, storage, manufacturing, and this can be for materials and also just all of the handling processes. And like I said, we have fewer conditions in development and pilot stages, and this really needs to be understood well if you're going to take those results and then scale them into mass manufacturing. Some materials are also more moisture sensitive than others, and some materials retain moisture more than others, and it's harder to remove. In some cases, these issues are obvious, slurry gelling, or really dramatic performance differences. But then other times we may not. What's the impact of very small differences in moisture levels? Is it really possible to measure? So this is actually a real internal project that's ongoing right now. All the data I'm about to show is actually hot off the presses, analyzing these in Voltaiq and pulling them into this PowerPoint just this week. So we did this with 1 amp hour stack cells on our pilot line with commercial materials. And then I'll talk about how these materials went through their manufacturing. And we know that moisture within cells can cause reactions with electrolyte, cause gassing, and it can cause surface reactions and impurities, structural changes to NMC cathodes. So I'm going to go through some details here. This is going to be an in-depth case study. So we use NMC 811 cathode, so higher nickel, maybe a little more sensitive to moisture. Synthetic graphite anode. In our environmental conditions, our slurry mixing is less than 5% relative humidity. Our coating head is less than 5% relative humidity. Punching, compression, those in-between steps from coating into really assembly and welding, etc. This is where we have a little bit of exposure to ambient environment, which this time of year in our facility, which we control as best we can, is about 20 to 30% relative humidity. And then cell assembly, we're in a dry room with a minus 30-degree dew point. So the drying conditions, what we do with these electrodes after they're coated is we do dry them, and we dry the cells. Cells assembled without drying compared to cells vacuum dried at 100 Celsius for 16 hours. And then drying the electrodes separately, assembling the cells, and then drying the cells all together. And you can see with some in-house Carl Fisher measurements over here that you can see the effects of drying, where we were able to pull out 30 to almost 50% of the moisture out of the cathode materials. And anodes retain moisture a lot more than the cathode materials. These are also coated with water in the slurry. But again, we're able to reduce the amount of moisture in the anodes. So what's the effect of this? It's a fairly small difference in some of these cases. can we see the effect of this? Does it really matter in cell performance? So I'm going to show some formation data, and all of this formation was done on our UHPC cyclers. So you can see here the differences between charge and discharge, and these statistical diagrams are very nice to show the consistency of the cell builds, and then how this translates into Coulombic efficiency. And you can see all of these cell builds are quite consistent with really tight tolerance on Coulombic efficiency. And you can really see the effect here of not drying the cell with a lot lower of a Coulombic efficiency, almost a % difference. And then just cell drying to then drying the electrodes, or drying just the anode and then the cell, which have about the same Coulombic efficiency. But there might be a statistically relevant difference in the consistency of when the anode group and the cell group were put together. And this is actually really important for the final conclusion here. So using UHPC for formation, we're really able to see CE measurements of accurate to less than 50 ppm. So these deviations that we're looking at here, even though these are really huge blown up scales of only a fraction of a percent, these are real differences that we can measure with UHPC, which is why we do some of these formation measurements on UHPC and see these differences very quickly and accurately. Another really good benefit of using UHPC, as I've mentioned before, is DQDV. So you can see here, when we blow up this DQDV, we're seeing some normal noise that you may be used to seeing when you look at DQDV. But with UHPC, there really is no inherent noise like this. We don't smooth any of our UHPC data. A good cell should have almost no noise within this curve. So anything that you see here is actually real. And we can see as we move through these groups, the consistency within all of these traces increases as we get to this final group. Especially the not dried group, there's a lot more noise in here. So these are talking to excess capacity during charge. If we have more area under the DQDV, then we're having more reactions happening, more capacity that we're counting at that voltage. So we can see and identify some things here, and this could be used as some kind of advanced metric to say, what is the noise between groups of cells? And then, of course, cells can go on to cycle aging and cycle for hundreds of cycles. All these cells, there's 12 cells shown on here, and there's really no appreciable difference in the first 6 weeks of cycling. We're waiting and seeing if we can learn something, and we're just going to keep waiting for a little while, not look at what we can see with UHPC in only a few days. So again, this is standard cycling, C3, C3 on a normal cycler. While this is going on, we threw everything on UHPC. And this is where we can start to do what we did with the cathode study and split up CE and fade slippage, see what differences we find. So here we've got Coulombic efficiency, and we can see there's almost no difference between any of these groups in Coulombic efficiency. And again, this is a very expanded scale, 99.8 to 99.94. So there's very little difference here, and especially the variation between the groups, there's no difference in CE. But when we split this up, we can actually see there are differences between these groups. These not dried cells actually have lower capacity fade. This is likely due to forming more SEI. We saw that they had a lower first cycle efficiency, so more lithium went into forming a thicker or robust SEI on the anode surface. So maybe this makes sense that this capacity fade is a bit lower. So why was its Coulombic efficiency the same as these other cells? And that's because the charge endpoint capacity slippage is higher. There are more of these slippage-based mechanisms happening in this cell due to that moisture exposure. So we can't really let the Coulombic efficiency fool us because there are differences in these different mechanisms happening. And then there's basically no difference between the cell only drying and the electrodes, drying both electrodes in the cells groups. But again, this anode plus cell drying, so drying the anode and drying the cells once they're assembled, has a lower charge endpoint capacity slippage. And so I mentioned that was an important note earlier. And digging back through, what was done when we dried the electrodes, what we found was that when we dried all of the electrodes together, all of the electrodes, the cathodes and the anodes, were put in the same vacuum oven. So as we're extracting all of this moisture from the anodes, in that same environment at elevated temperatures, these cathodes are getting exposed to that moisture. And that's what we're considering here is this effect that's making basically the cells that were dried without drying the anodes and cathodes and the ones where all of the electrodes were dried together performing exactly the same. Because in both cases, the anodes and the cathodes exposed to ambient moisture are put in the oven and baked together and exposed to the moisture that's trapped in the anodes. So in this case, the anodes were baked, but they were put with fresh cathodes that hadn't been baked with anodes before. So our takeaways from this were that the removal of anode moisture prior to cell drying mitigates these slippage-based mechanisms and improves consistency in our cells off of our prototyping line. And these slippage-based mechanisms, as we've seen before, these lead to early cell failure. They lead to things like electrolyte dryout, lithium consumption out of the electrolyte. And these can be due to electrolyte reactions with surface contaminants on the cathode after reacting with moisture, lithium residuals, etc. And then we also have as a conclusion from this that cathode electrodes can't be dried in the same oven as anode electrodes. And we were able to make these conclusions and see these differences just in a couple days, rather than waiting weeks and weeks until we see something appreciable happening here. So that was a pretty in-depth, and of course it's an ongoing study here, but shows just how we use UHPC to make very quick insights and not have to wait months and months for those data to show us what we maybe saw in just a couple days. So another case study I'm going to go into just for a minute or so, I covered this last time as well, is 18650 filling and formation quality. So obviously this is a big step in ensuring good quality of manufactured cells. So taking your cylindrical cell and making sure that you properly wet it before starting to charge and access all of the anode and cathode materials. So the challenge here is potentially having low yield, inconsistent capacities, and again, always long development and validation times. It may take a while to end up seeing some of the effects of this. And so when we were trying to optimize our vacuum staging protocol for injecting electrolyte and then pulling vacuum for certain periods or vacuum levels, what we did is we used UHPC just in this very first step of formation, where we do a 1.5 volt voltage hold and measure and monitor the current supplied to the cell to maintain that voltage. And the more consistent that current is and lower at the end of that voltage hold means there's less material there's more consistent wetting, and there's not continued wetting of new material within the cell. And we found very quickly that this wetting step, measuring the current very accurately through this step to microamps levels, and of course these are accurate to nanoamps on the UHPC. The consistency here correlated very well with the first discharge capacity and the consistency of cycling down the road. And so we were able to take something that could take weeks or months of cycling a cell to figure out if there's going to be some plating in it or leading to differences in fade, and turn this into less than a day of turnaround from trial to results and iterating on the next step. So the final case study I'm going to spend some time talking about is getting into the weeds of manufacturing QC. Just doing a quick time check. So we've mentioned that speeding up cell quality with great accuracy is a big industry need. QC results take weeks, days to weeks of storage, as Kevin was talking about, and these OCV or ACR measurements are really the meat and potatoes of QC checks. We can't put every cell, a million a day coming off of a gigafactory line, onto a channel and measure it during QC. So we have to do these quick one-off checks after storage periods. So these millions of cells stored at any given time create a large footprint and OpEx for companies. So this proof of concept study that we did was to see if UHPC can speed up this QC process. So we had a client state once that an ideal QC passing self-discharge rate would be equivalent to something like C over 100,000. If we were able to detect whether a cell was self-discharging at that rate quickly, then this would really rapidly speed up their QC process. However, this can be difficult because these storage conditions are in massive warehouses and the temperatures can fluctuate by plus or minus 4 degrees or so. It's very expensive to keep a very stable temperature within these large facilities. So our goal was to measure this self-discharge rate, prove out some cells that have already passed QC, and then prove a route to more rapid QC process. And this is more of a case study thought experiment than really fleshing out what could be a new QC method. And of course, thinking about it in terms of every cell cannot be connected to a UHPC channel, that would make for a very expensive QC facility with millions of UHPC channels. So this would be more relevant for intra-batch statistics. So we did these tests on these 120 amp hour LFP graphite cells and operated at the endpoints of what was considered to be that storage range and did 3.6 volt CCCV testing from C over 6 on a 20 amp circuit, UHPC circuit, and then trying to test down to C over 100,000. So this proof of spec, a 4-day CV, so over 100 hours, we put these cells on test and did a constant voltage, hold at 3.6 volts. And by about 40 hours, we confirmed this kind of factory ideal QC. All the cells came under this. Well, the line is not where it should be right now, but came under this 1 milliamp hour point here. Even the 29 degree, 22, both of them were under that line. So that's what we're assuming is this ideal QC ability. So even now we're saying just in 4 days, instead of say 2 weeks, maybe we're able to do this when we connect a cell to UHPC. And then here it's important to look, even though there's some noise here, the current precision and accuracy of UHPC is capable to tens of nanoamps. So this isn't just noise and inaccuracy. This is real measurements of the cell and fluctuations that would happen. A note here is that when we think about doing a voltage hold, even though these currents they don't look super small, based on the size of this cell, remember it's 120 amp hours. This is C over 100,000. The DQDV of this cell at these voltages are anywhere like from 1 to 200 milliamp hours per 100 microvolts. If your cell tester is not accurate or precise to much better than 100 microvolts, and you're bit switching or something within trying to hold that cell at 3.6 volts, you'll make massive swings in current or generate lots of noise in your current signal. So this voltage precision and accuracy that's capable with UHPC is actually really important to make this happen. If this test was done on most other cyclers, the noise would be off of this chart. So when we looked at this data, we said, okay, great. The 30-minute average current at the end of this is C over 200,000. And then the variability between those two cells is plus or minus C over 4 million. These are odd numbers to be throwing out. We don't necessarily think of C rates as that, but it's more relatable maybe than transferable between cells than the actual magnitudes of the current. So how fast can we make this happen? So if we now shorten that time and look at maybe just the first 15 hours of that CV hold, we can see the 29-degree cells, maybe their kinetics were a little faster, so they dropped in current and then stabilized. And then the 22-degree cells followed suit and stabilized around the 15-hour mark. So maybe we can use that. We can see that these are also very stable or very consistent between the cells. So the hope here is that a correlation to this steady state ideal current of 1 milliamp can be made fairly consistently with an order of magnitude better variability in the cells than the actual target self-discharge current. So taking this with a larger statistical size of cells, and then proving out that within only 15 hours, let's say, we're able to accurately and precisely get the same or better idea of what cells would pass QA, QC is actually going to be, theoretically with the accuracy and precision that we have in this current measurement is going to be possible. So these inter and inter-batch statistics with only maybe a few cells per lot could identify lot-to-lot variations with very extreme tolerances to be able to identify, hey, this super sack of cathode may have had a different, when you look through all the metadata connected in Voltaiq, like Kevin showed, was linked to this batch having a slightly higher self-discharge rate with very high confidence just in 15 hours of testing. Or even within one batch, doing a statistical test with a relevant number of cells, tens to 100 cells, to show what that band actually looks like, and is that band acceptable in only a very short time. So this is just another way of looking at those data to show that the level that we're looking at in only 15 hours, we're very accurately able to measure the differences between these cells. And there should be a path to making QC happen, not just in this 100-hour CV hold, but even just a few hours, less than a day, using UHPC. And again, really important to consider that this has as much to do with the current accuracy and precision as it does the voltage accuracy and precision in actually holding the cell at that voltage to keep that current steady. So one last thing I'm going to cover is something that I've mentioned in the previous two webinars, just looking at lifetime prediction. Obviously, these advanced metrics with coulombic efficiency, slippage, capacity fade at these levels that are previously almost impossible to obtain, maybe we can layer these into machine learning models and create transferable models between slightly different chemistries to predict lifetime. So this is a case study that we did with partner Sandbox AQ, and really working with a couple different cell chemistries or cell vendors with cells with all high nickel cathodes, but different anodes. So some of them contain only graphite, some of them contain graphite and a bit of silicon, operating at different temperatures and different voltage ranges to turn on and off some of the failure mechanisms to make it really hard to make a generalizable model for lifetime prediction. So operating in ranges where we don't use the high voltage end of the high nickel cathode, using the full range, and then even cutting out some of the silicon capacity in lower states of charge, and then of course those different temperatures. So I'll keep this fairly brief. Using standard model features like in the Severson model, using delta QV voltage feature changes, cycle 1 to 100 discharge capacity trends of cycle aging data, especially when we're using things like that have silicon, that don't have silicon, using high temperature, high voltage, high nickel cathodes, and then lower temperature and not using that part of the cathode. These models don't do a very good job at predicting lifetime. However, when we layer in UHPC testing and use these UHPC enabled metrics like slippage, really high precision coulometry, and layer these in as an additional feature to the early cycling of standard cyclers, we get really good model performance using these advanced features. So this is also something that can be enabled by UHPC, and this is also some ongoing work that we're hoping to publish more on. So I just want to come full circle to one of my first slides, talk about the conclusions here that UHPC, what we're trying to do with quality control is look for small things with big implications. So hopefully it was fairly obvious in some of these case studies that you can detect very small things very quickly before you'd ever be able to with other cycler types, and that we're really working to address these gaps. And it's a valuable asset in any lab. And I said before, I have thousands of cyclers in this facility here, and only about 10% of them are Novonix UHPC. The other 90% are lower resolution cyclers that are doing all these other things amazingly, and we all need these things. But it's a really great tool to fill those gaps and get insights very quickly. The final question I just want to ask everybody, especially those that have been to the other webinars, is where you think UHPC has the biggest potential impact in research, QC, process development, or manufacturing. I'm not putting in all of the above here. I want to hear some subjective opinions. So go ahead and vote. All right, so it seems research and QC definitely went out. So that's good to see. And yeah, so with that, I'm going to finish off, and I think we're going to dive into some questions. There's lots of time left. Yeah.
Thanks, Stephen. All right. So there were a couple quick questions. The first one, and I did answer this one, but I'll take it real quick, was, is there a way to plot some of these UHPC metrics in Voltaiq? And Stephen, the one specific case study that you gave talking about the moisture contamination was all done in Voltaiq, correct?
Yeah. And also this one here, the filling and formation.
Okay. Awesome. So yeah, all of those metrics, Voltaiq has a very robust platform for being able to create and perform all sorts of metrics. So UHPC is a set of metrics that we offer to our customers. There's also the ability to customize those metrics. So for specific manufacturing processes, or for if you have some specific metric of interest that you guys have developed that you want to track as part of manufacturing or research or whatever, any of those metrics can be calculated within Voltaiq. Okay, some of the other questions here. There's a common theme about these taking a long time, being at lower C rate, and kind of general practicality in terms of being able to extrapolate that towards higher C rate capabilities. Do you want to just speak to that, and then maybe I can dive into a couple questions?
Yeah, for sure. So looking at one here. Yeah, so UHPC, the question was UHPC is limited to test at low C rates and very precise temperature controls. How applicable is the result of high C rate cycling? Yeah, and then looking at is it still applicable for larger cell format? And I think the answer to a lot of these questions are the classic answer of it depends. For number one, higher C rate cycling. So it really depends on what the goal of the testing is. So in these cases, like this moisture study that I'm looking at, we're trying to find really tiny differences in the electrochemical reactivity between the electrodes and the electrolyte. So we're not really concerned so much with kinetic effects within the cell. We have other ways of probing kinetics like EIS or DCIR that are all really great methods for that. When we want to measure what the effect electrochemically is, the best way of doing that is removing the effects of kinetics. And this is why we do these slower tests, so that you don't have variation in where your charge and discharge endpoints are relative to SOC. So you don't have as much self-heating necessarily within your cell. And we're not really worried about the effects of kinetics. So even cycling slower within, say, a 10-hour charge and discharge, you're allowing more reactions to happen. So your actual signal to noise of the degradation mechanisms happening is larger the longer you let that cycle go for. You're allowing more of these slippage-based mechanisms to be measured for the same capacity of cell of lithium that you're actually moving across and trying to charge. So you're increasing that signal to noise of electrochemical impacts. If you're trying to look at the mechanisms that are driven by kinetics, you can definitely use UHPC at higher C rates. So in the last webinar, you can find it on Voltaiq's YouTube page. I looked at the effects of cell orientation on electrolyte pumping and how that would impact performance long term. And in those cases, we were actually testing cells C/3 and 1 because we were looking for differences in slippage or in coulombic efficiency that would be driven by kinetics. You can also do that with this for detecting lithium plating. Obviously, if you're starting to plate lithium, you're going to see that in your discharge capacity and your coulombic efficiency. And since we can measure that very accurately, you see it very clearly, very early, even the tiniest changes with effects of lithium plating. Again, it depends on what we're trying to look at. A lot of these use cases I'm showing, we're trying to kick out kinetics and try to look at electrochemical impact or self-discharge impact, which kind of leads to that last question, what's the limit of cell size or C rate where the effects start to deviate from normal cycling test results? Again, that kind of depends on the tests that are being done. But in this specific test, I'm doing this on a 120 amp hour LFP graphite cell. The max I can cycle this cell at with our current systems, which go up to 20 amps, is C/6, but that's still plenty relevant to do these like QC-based tests, get a cell up to a voltage range, and then start going into that CV down to these like really low currents.
Yeah. Yeah, there's a lot of really interesting the C rate. I love to think about C rates and the current that's applied in terms of driving force. And just the driving force is very different when you have low C rate versus high C rate. The driving force is different. And so the types of reactions that you can drive are different, but those reactions are all still there. So when you go to a high driving force, if you're going to go to a high C rate, you may activate new reaction mechanisms and new things may happen, but those underlying reactions are likely still going to occur that you're uncovering with some of these slower C rate sorts of things. So once again, like we've said in this, you need a variety of tools in your tool chest, and you have to understand how these different things interplay and intertwine but together to really understand how the cells are going to perform ultimately at the C rates and lengths, time scales, right? Lifetimes of the application that you're targeting. Okay. There's a question here. It says, are those differences in capacity slippage that can be seen in days, would we expect those trends to be the same after months and cut short the testing instead of long-term testing? So I maybe I'll let you try and interpret that question and then see if it jives with my interpretation.
Yeah, sure. Yeah, a lot of the time we don't really see, especially when we're doing very apples to apples comparisons, we're not changing cathode materials or anode materials between these comparisons. What we see is these trends continue more or less. If we were able to measure these infinitely accurately and precisely, we would see these trends continue together. With UHPC, of course, there is going to be a limit, and especially the consistency between the cells will reach a limit at which, these all more or less within error coalesce. But to like the reality of UHPC testing is these channels are a lot more expensive than other channels. So we really try to tailor what tests we do on here and do these kind of rapid screening tests where I show 25 cycles here. This is a few weeks of C/10 cycling, but we could do this in a week, just do 10 cycles or so, and then call it quits after that because we've got our ranking here, we've got our interpretation, and we can move on to the next iteration. We wouldn't necessarily keep these cells cycling for thousands of cycles. That's what we would do something with one of these other types of cycling systems.
And what happens in the very first few cycles is really important and critical for how the battery will ultimately perform. And that's what you're probing here. Yeah. Okay. There was another question. Samsung is going through a massive recall right now. How do you think UH would have helped prevent this situation?
Yeah, and I think that's where this last kind of case study or thought experiment here comes in, is really trying to understand I don't know if anyone in this call really knows the answer to how finely would we have to detect differences between cells or lot-to-lot variation to be able to detect those specific types of recall features, a folded over separator or something. Is that going to show up in something like a current measurement where we're looking for self-discharge within the cell? Is it going to show up more to do something like impedance? But this is an example of somewhere where this type of really fine, detailed measurement is not really used in any mass manufacturing QC labs. As far as we know, there are lots of tier one manufacturers with this equipment, but not necessarily at the levels that would be relevant to see hundreds of cells within a run. Is there some kind of larger variation, just like you showed, Kevin, with the delta V? Those things are easy to measure, but with obviously these recall issues didn't show up in those types of traditional metrics. So what can this gain us, especially since we can do it a lot faster, and those cells aren't already going into packs and into trucks and cars by the time they're detected? So I would say how I think UHPC could have helped is investigating things like, now retrospectively, find all of these things that have caused these big recalls in the past. And it seems inconsistent separator alignment and folding and stuff is being a common case in a couple of these instances, and try to see what UHPC can be used to detect that if there are inconsistencies or different in the shape of how the current moves here or the final value. Unfortunately, I can't speak to exactly what if this specific method would work, but I'm pretty confident we'd be able to do something because we're able to go that multiple orders of magnitude deeper than traditional QC and test equipment can.
Yeah. Yeah, and I think that this is part of what we were talking about, or what I like to talk about with that battery iceberg, right? It's more of these processes and things that you're able to put in place to help you mechanistically understand being able to create traceability back and really help improve the tolerances and the process controls that you have in place is really what's going to help you prevent these sorts of things in the future. And hopefully each time you go through something, it's a learning experience and you're able to improve your process control so these things don't happen again. And we identify those things sooner and with less significant consequences. And that's really the whole goal and mission of Voltaiq and what Novonix can provide from the UHPC side as well. All right, there's one quick one here and it says, considering the good detection limit of UHPC and DQDV, has Novonix or Voltaiq started to build a list of known side reactions and peaks that are attributed to an active clean material versus not? And the answer to that question is yes and no. So there's a lot of great knowledge out there in terms of like DQDV peaks. And you could even go back and listen to when we talked about extracting and pulling out the details of what is actually in those DQDV peaks, right? So the thing that I would say is that, yes, we can go through and say, if you have a peak at 2.1 volts in your very first formation cycle, what is that actually telling you? There's a lot of really important and interesting information that you can extract there, but it may be different from process to process. What's happening depending on your anode and cathode, depending on the potential of that reaction. And there's a lot of moving pieces there. There are tools that can help you figure out what the individual reactions are, but a library of like side reactions is a little bit more difficult. Voltaiq does provide a kind of a side reaction metrics and some of its advanced metrics that can be provided that can help you identify those things, but telling you exactly what reaction it is right now is not something that Voltaiq does, but we do surface side reactions and do provide a lot of information about those at your fingertips. Stephen, do you have any other thing to add to that?
No, I think that was a good description. I think we've talked about how it would be interesting to build up certain libraries and materials and stuff before, but I'll just around a table with a coffee or something at conferences. So something we can keep talking about. I've got two more here that I'm going to go into.
Yep.
Does Novonix provide a trial of the UHPC tool? Definitely reach out to us. So we do have some options that we could talk to you about. And this next one in R&D scale, sometimes batches of cells can have different internal resistance, which could cause different temperature rise during charge or discharge. Could this cause troubles for UHPC measurements? I would say, again, it depends on the tests we're doing. I'd say if there were that big of internal resistances, if we're saying some batches of cells in terms of trying to do QC on one over another, I think that would be detected earlier on. But if we're even talking about just in general, it does internal resistance, self-heating matter for UHPC measurements. I'll say in general, yes, it does. Of course, if you are increasing the temperature of your cell, you are decreasing that kind of like inherent hysteresis that eventually, your cell's going to cut off, say at your upper cutoff of 4.2 volts. If your cell is warmer one cycle than the next, or one cell is at a warmer part in a chamber, let's say, than another, then it's actually going to terminate at a slightly lower SOC than a cell that cycled a little warmer. So if these variations in temperature are happening in your cells, then yes. And so that's why doing really rapid cycling and trying to measure coulombic efficiency, you're going to start to see a lot of noise generated in your coulombic efficiency measurements. And these aren't because you're not accurately counting the electrons. This is because you are charging a little bit more one charge than the next discharge, and then the next cycle kind of making it up with a shorter charge and a longer discharge, because we're not very cleanly terminating the charge and discharges at the exact same SOC point every single time. And that's just an effect of kinetics in general, regardless of self-heating, just concentration gradients within the cell. If you go from really slow to really fast, it's going to take a while for that CE to really stabilize or come down and stabilize. So there are a lot of considerations there when you have the ability to measure Coulombic efficiency and these things that accurately, then all of these like kinetic contributions to what it means to measure the amount of electrons from exactly 2.8000 volts to 4.20000 volts is really important.
Yeah. Awesome. I think that concludes the Q&A portion. Just one more question for all of you out there. Would you please let us know if you are interested in any of the following? So if you're interested in talking about Voltaiq's analytics platform and some of the analytics we can provide and the traceability that we can provide, let us know about that. If you're interested in some of the consulting work that we do in terms of helping you understand, hey, what are these peaks that I'm seeing in my DQ/DV curve during my initial formation cycle or anything like that. We provide a range of services around that. And then Novonix, are you interested? One person was saying like, hey, we're interested in a trial of Novonix C systems. Please let us know. Any of those sorts of things. If you have other questions or whatever, just select one of these boxes and we can get back to you. It's been great chatting with all of you. This webinar series has been really helpful for me. I hope it's been the same for you as well. So hopefully we will see you at a conference or in person sometime soon. Thanks, everybody. Have a great rest of your day.
Thank you.